Welcome to Stajano Explains. Today's topic is Java programming. I have here for you a purposefully buggy piece of code that comes from a past exam question for the Object-Oriented Programming in Java course. And your job at the exam was to critique and improve this code according to these various sub-questions over here. Now, at the time that I'm putting out this video, we are still rather far from the exam season in June, so it's worth concentrating at this stage on acquiring the right programming skills as opposed to learning how to answer exam questions in an exam setting. And I've done other videos on, answering exam questions, and I'm sure I'll do some more. But today, let's concentrate on the programming side without too much concern for the exam. So today, I'm trying to help you become better programmers. If you enjoy this, stick a like on this video and subscribe, you know the drill. Okay, so what I want to do today is to engage with this problem, but on the computer, writing code that actually compiles and runs, and then doing some testing to find some of the other bugs you probably still have in your code. And this may take you a few hours depending on how deep you go down the rabbit hole, and you certainly don't have the luxury to do that in an exam, even if you were an exam where you were allowed to compile and run your code and test it and so on, which is clearly not the case. So in the exam you have about half an hour, so you have to just get to the ideas and the core intellectual content of the question, and basically you primarily try to show that you understand the principles, and maybe you still get most of the marks even with code that wouldn't compile if you tried. Whereas today our focus is on actually writing good code that works, and works all the time, including the edge cases, and picking up some hints about good style, so to say. So here's the code. Have a good look at it. Stop the video, figure out what it does without trying to compile it, and then list all the things it does wrongly and rank them in order from most serious to most trivial. Then, with this list at hand of things you dislike, load this code into your editor and fix all the bugs you found, or all the things you didn't like. And also write suitable tests to persuade yourself, use unit testing to convince yourself that the stuff you fixed has actually fixed the bugs, hasn't introduced new bugs, and it all works the way you intend it to work. So please do this yourself before going on with this video if you want to get the most out of this exercise. Now, I should maybe have a little aside saying, well, we are on YouTube. The kind of video that gets lots of views on YouTube is one where the viewers can just sit there with a popcorn, watch me do stuff, and be entertained. So this video will fail miserably in that respect, because it requires you, the viewer, to get off the sofa, leave the popcorn aside, and do something. And if you don't do that, then it's not going to be an especially entertaining video. So most viewers will switch off very early. Only an elite minority of the viewers will actually stop the video when I say so and do the work before watching how I solve it. So I don't expect this video to collect many views or to have very high retention of people watching until the end and so on. But I do trust it will be a useful video to those few good ones of you who actually do the programming work, instead of just thinking to themselves, yeah, I know, go on, I know how to do it, and then watching passively. And my video being actually useful to those who put in the work to learn something is worth more to me than getting high YouTube watch metrics and all that kind of stuff. So, okay, end of my rant. Now, actually, please stop the video, figure out how this example code, I meant to highlight, but never mind, I meant to do this, how this example code works, and list everything you think is bad with it, then code up a version that fixes all the bugs you found, and then come back so that we can talk about what we considered to be the worst bugs, see if you consider the worst the same as the ones I consider the worst, and how I had to go at fixing them when I did this work on my own, because I did. Okay, that was yesterday evening. So stop the video and see you later. Stop the video. All right, welcome back. So what does this code do first of all? Well, what it does, as the name suggests, is implementing a fixed capacity queue of elements. Here the elements are integers. And we mean first in, first out queue, FIFO queue, the kind of queue you find at the supermarket checkout counter if people are polite. Americans would call this a line, but we say a queue. Okay, so let's have a little piece of artistry representing our queue. So this is the checkout counter, and there's a person here with a kind of adding machine or something produces a till, and then there's people who come here with a thing full of groceries. There's another one here and another one here, and so this customer here is at the front of the queue, is the first one who's going to be served, who's going to have their groceries added up, and that's the last one in the queue. And so in the terminology of this class, we call this the head of the queue and this the tail. So we have an index that points at the head and an index that points at the tail, and all these things are held in some kind of array called mdata, where there is space for 3 and maybe a few more. So that would be low battery on this tablet. No. What I meant to do was to draw an array here like this that has space for these customers, and this array has a fixed capacity, as the name of the class suggests, this capacity that I set up here in the constructor, and this capacity is finite, and at some point if more people come in and say, well, sorry, we can't fit any more in this queue. So to put people in the queue, then we have a method called enqueue, which basically sticks them at the tail end of the queue, and presumably will fail if I reach here with all the other places filled up. And then we have dequeue one, which is when the previous customer has paid for the groceries. Then the head of the queue can be dequeued, and then there's a gap here left, because then the new head of the queue is going to be this one. Okay, and so of course we observe that these methods cannot always work. The enqueue method will fail if the queue is full, and the dequeue method will fail if the queue is empty, and attempting to do either of these things, calling enqueue on a full queue and calling dequeue on an empty queue, is a mistake, and the code has to tell you about it. So, is there anything that we don't like about this code? Some of the things we don't like are poor style, and some of the things we don't like are actual mistakes. So let's deal with the worst stuff first. What's the worst thing that this code does? Well, personally, I would say the worst thing it does is that when you dequeue and the queue is empty, this method returns -1. It tells you there's a problem by giving you this magic value, -1. But that's a particularly stupid choice, because -1 is actually a perfectly valid integer. So it could be one of the elements that had previously been inserted or enqueued into the array. It's perfectly legitimate to call enqueue with a value of -1. And when I take this out, I have no way of telling the difference between returning the previously inserted element -1 or returning this -1, which signals, oh, you tried to dequeue from an empty queue. So that's a very poor design choice. That's clearly a bug. Now, does this happen anywhere else? What happens on the enqueuing side? Well, on the enqueuing side, the person who wrote this class decided instead to signal the error by using the return value of the function. So here they return false when the mtail is equal to length, which in their intention is when the queue is full, and they return true when it actually did work. So at least it's less bad than returning a -1, because it can't be confused with a legitimate termination of this method. Why didn't they do that with dequeue, just returning true and false without confusing with the elements? Well, because dequeue, when it works, needs to return the value that gets dequeued, whereas enqueue doesn't need to return anything. So you could use the return value for this Boolean, and you couldn't use the return value for a Boolean because you needed to use it for the value that came out. In Java, it would have been pretty cumbersome to return two things at the same time. So that's why this strategy was not adopted in this one, besides the fact that they wanted to put in some kind of bug for you to do some work at the exam. Anyway. However, this idea of returning a Boolean that enqueue uses, while it's not as bad as returning -1, is still bad, because every time the calling code invokes this enqueuing method, it has to check the return value in case it's an error, because it could be an error some of the time. And if it does this check, then the source code becomes a mess, and the logic of the program is hidden in a forest of if statements. If the return value says there was an error, then do this, which most of the time don't get executed, but they still clutter up the code, and when I review it, I can't really figure out what's going on. If instead the calling code doesn't test the return value, that's even worse, because errors go unchecked, and they might cause spectacular crashes. So that's a very poor programming style, using the return value of the function to say if there had been an error. And it's the kind of stuff that old school C programmers would write. But we are now in the 21st century, and all modern languages have exceptions, and there's no excuse for not making good use of exceptions. So both of these functions should be fixed to use exceptions rather than return codes in order to signal that there was a problem. And if this were a closed book exam setting, then you'd get most of the marks for explaining why we need exceptions and kind of highlighting where they would go, even if you couldn't remember all the exact details of how you declare and throw an exception in Java. But we are not in an exam setting. We are in a setting of wanting to produce working code. So you actually do type this into your editor, and if you get the syntax wrong, then it won't compile, and you'll have to remind yourself of how to do it properly, and possibly with help from the development environment itself, which will suggest the correct syntax where it's easy to do. And that's the thing you should be doing now, the thing you hopefully did before restarting the video, because if you become proficient at this now, then come exam time in a few months, you will confidently know the right statements to write to throw an exception, even if you are in a closed book exam setting and you can't look it up. All right, so let's replace these stupid return values with proper exceptions. So this is what I've done for the worst one, which was the dequeue. Instead of returning -1, I throw a new empty queue exception. This is an instance of a class empty queue exception, which I have to also declare somewhere. And so somewhere else I'll have a file with this class empty queue exception over here, which extends exception. And the reason that exceptions are made into classes is precisely so that you can have a hierarchy of them, and you can make sub-exceptions, which are subclasses of some more general exception, so you can then decide which exceptions to catch, and you can catch a whole group of exceptions by going higher up in this tree that you define. Anyway, so you define this exception as a class over here. You throw a new instance of this object, and you have to declare that your method might throw this exception. That's how it would look like. And then we do the same thing with the other one. So where is it? This one is the enqueue. Okay, try to align with this. The enqueue method over here, I substitute this return false with, in that condition instead, I throw a new full queue exception, which I also have to declare somewhere, same as before. And I declare that this method enqueue might throw a full queue exception. This one throws empty queue, this one throws full queue. Okay, and the rest of the code stays the same. All right, so which things did we not like besides the fact that dequeue was returning -1, and both of the dequeue and enqueue were using their return values for signaling errors. The next thing we don't like is that this code makes very inefficient use of storage space, because basically it uses each of its cells only once. All that happens to so if I redraw my queue here again like this, then we begin with M head starting here, M head, and then the M tail also starts here, and at the moment they overlap, but they can move around. So if I insert something here, if I insert first blob in here, then this would be NQ, and M tail is incremented to point to this other cell. So this is the head, this is the tail. If I insert another one, another round of NQ, then I insert in the position pointed to by M tail, and then I increment M tail. So I insert in here, and then I move the M tail to point to the next cell. And that's all great, and I can see this process going on. What happens when I dequeue? Well, it says I'm going to, over here, extract the value pointed to by head, which in this case would be this, and then I increment the head. So I will extract this value, means that's the thing I'm going to return, and then I am going to move this pointer here. Now if I enqueue another value, it will go here and I will move this. If I dequeue another value, that's the one that will come out, and I will move this. But if I keep doing that, and let's say now I have one element logically in my queue, even though there's 3 blobs that have been drawn in here, but these ones have logically been extracted from the queue, even though I haven't blanked out those cells. If I keep doing that and I insert one more and extract one more, so I do enqueue and enqueue, yes, and dequeue, enqueue, and dequeue, enqueue, and dequeue, then my my queue would always have either 1 or 2 elements inside it. But as I keep doing that, these things will move by 1 like this, until we get to the end. So here we are at the end, and I do this this operation until I get here. And what happens? Next time I try to do an enqueue, it will say m data m tail equals x. So I'm going to insert something in here. Then it's going to increment my m tail, and so that would bring my m tail to outside the array. Next time I dequeue, okay, that will still work. We'll move this thing to here after having extracted the thing that was in this cell. But at my next enqueue, I will run into this part, which says if m tail is equal to m data length, and this is like 0 to n minus 1, this is going to be n, so this is going to be n equal to the length. And it will say, no, sorry, the queue is full. But it's not full, it's just that I've reached the end, and all these other things are empty. So the logical capacity of the queue is far from exceeded. It's just that I run all the way to the right, and this is clearly bad. So how do we fix that? Well, the question setter thought of just moving things around. Every time you dequeue an item, instead of shifting the m head to the right, what he suggested is you could just leave it there at 0 and shift all the others down, because you've now created an empty space here. So that's very easy to implement, but it's rather inefficient, because every time you insert an element, you have to shift to the left, potentially up to the whole array. And that's pretty bad, given that you could achieve the same result without moving anything around. It's enough just to make the buffer circular. You can imagine that if you view it from top, instead of looking like this, you can wrap it around to look like this. and you have indices that chase each other around this donut, and it doesn't matter where they are. You can do that just by using modular arithmetic on the indices. And of course it's very easy to say that, and many candidates said that, but apparently the candidates who said that at the exam tended to get the details wrong, so that their code wouldn't actually do what they claimed it should do. So you have to balance the tension between doing an inefficient design but then getting a correctly working solution versus suggesting a better design. Clearly the one with the modular arithmetic is a better design, but not being able to implement it correctly, which is kind of shameful and a pity, because in the end what you want is a program that works instead of crashing or giving the wrong results. So to get to a correct implementation, it may take you a few rounds of trying things out and see it on small cases, and ideally doing unit testing, which of course you don't have the luxury to do at the exam. But while we are talking about correctness, one of the things I didn't like about the code that was originally suggested, and it's one thing that many other people might completely ignore, is that some of these comments at the beginning are wrong. Okay, so this says m head equals 0. M head is the index of the first full cell. M tail is the index of the next empty cell. Well, this description of what these fields are contains falsehoods. It is not always true that m head is the index of the first full cell, because, for example, when the queue is just created, then there are no full cells, so you cannot have the index of the first full cell, and it's wrong to state that m head is the index of the first full cell if it is not always so. And similarly, when is this statement wrong? Well, index of the next empty cell, if there is no next empty cell, because all the cells are full, if the queue is full, then m tail cannot be the index of the next empty cell. So why am I upset about this more than most other people? Because to write correct code, you need to have, a good practice is to establish some invariants, some properties of your data structure that are always true, always correct. I mean, they may be temporarily violated within a method that changes the data structure, but before entering any method and after exiting any method, the invariants must always be true. This is clearly not the case for these statements here. So these are not invariants. And it's much better if you design your data structure around some invariants. So how would you fix this? Well, you could hack things to some extent by making a special case in the invariant. You say, well, if the queue is empty, then this is not true, but in every other case, then m head is the index of a full cell. And here you make the opposite situation. If the queue is full, then that's not true, but otherwise m tail is the index of the next empty cell. Okay, but how do we know if the queue is empty or if it's full? Well, you could think for a moment, say, well, when the pointers reach each other, then that must be that special case. But I think again, how do you distinguish empty from full? So at the start, these two pointers both point at 0, and it means that and we know that in that case the queue is empty. But what would happen if all the cells were filled up? Maybe also the two pointers would point in the same place, and how can we tell those two cases apart? Do we need another Boolean or whatever? So we need to do something to be able to distinguish this. And it's a good idea to try and write some simple Boolean methods of is empty and is full for your queue and see what makes sense. How would you write correctly working is empty and is full methods? Maybe you can have a try. So we had this discussion with some of my brilliant students here, and one of them said, I'm going to use an out-of-range value for the index. So this smells suspiciously of that mythical -1 that we disliked so much, but actually in this case it makes more sense, because -1 is not a valid value for an index that addresses things in this array that goes from 0 to length -1. So -1 clearly is distinguishable from any valid index. And so my student would say, I'm going to, for the case of DQ, where you could end up with an empty queue, I'm going to signal empty by having this head pointer here be -1. When this is -1, it means the queue is empty. And for full, I'm going to make this other pointer be -1 to signal that it's full. So I still have a gut feeling that this -1 is a bit disgusting, but I acknowledge that this solution can be made to work. Okay, so let's try to make it work and see what this entails. If you try to code up this type of solution, and maybe you already have, then you will notice why it was a bit disgusting to me, because you have to make a special case for this -1, and you have to keep checking this special case in a lot of places. And also, not just checking, you have to update it. If anything, if you do a DQ and this makes the queue empty, then whatever your head was at, then you have to add another statement that sets it to -1. And then next time when you're using the head, if it was a -1, you have to do something different. So you have to do all these special cases throughout the code, and sometimes you'll forget to do it, and sometimes you'll overlook that you also needed to check that, and so on and so on. And if you're doing this for real in a programming context as opposed to at the exam, then at least you have the luxury of being able to write some tests. So people who are not very good programmers think that tests are a major pain, whereas good programmers think unit testing is the best invention in programming since sliced bread. So I hope you all want to become good programmers. And so how are you going to use unit testing to check that all the stuff you put in does what you thought it would? Well, as I was writing tests for the code I had written up to that point, in one of my first attempts I said, well, if I'm going to check that it's doing what I want, maybe I want to see what the internal state of this queue is. So I want to be able to inspect the content of this array, which is not exported by this API over here. So to do that, I need to render this as a string, print it out with its own integers anyway in this toy implementation. So I can just print a sequence of these integers. So I had to write myself something that was outside this API, a method that transformed the content of this queue to a string. Okay, so of course I know that the array in here doesn't blank out its cells even when it's empty. So now this condition here is inconsistent, because if this at -1 signals that it's empty and this at -1 signals that it's full, it cannot be simultaneously empty and full, except perhaps if it had length 0 when it was created, which is something you should also consider. Should the constructor accept a length of 0? But anyway, let's not sidetrack too much. But anyway, let's pretend we are here. Then this signals in our convention that the queue is empty, but clearly there are numbers here, which are the numbers that I inserted throughout the lifetime of the queue before it became empty. And if I print the state in the way I described, I would want to see those various numbers, even though the queue itself is empty. So at some point I decided I should also print the logical view of the queue as well, which tells me not just what's in the array, but what the data structure thinks are the cells. And so in this case, it'd say, well, the raw content is this, but the logical content is empty. So this is the kind of two-string method that I did initially, where I just printed the things between square brackets, and I just iterated through all the content of all the cells in the array, and I printed them out. And then afterwards I came to use this in a test method similar to this. For example, I enqueue 5 values, and then I say, well, the state of my thing is, okay, the representation of the array is this toString, and then I have booleans that say if it's empty or full, and I record what they are. And then I do some more operations, and I record this thing in, this is version A, version B, version C. And then at the end I say, well, at point A I would expect the content to be this, and this boolean to be false because it's not empty and it's not full. And then after a few more operations I expect the content to be this, and it's not empty and it's not full. And after a few more, which cause it to wrap around because I want it to just wrap around, and I expect this to be the content, and so on and so on. So this is before I had decided that I also wanted a method that showed me what the logical content of the queue also was. But when I started modifying this to string to add the printout of the logical version of the queue, I realized that there was another hidden bug in my code, because I had failed to do one of these many explicit checks for whether the queue is empty or full. So that's the same code as I showed you before for toString, and then I had to fix it by adding lots of extra logic. This is the part that is the same as before, just prints the raw version, the raw content of the array. This is the part that between those vertical bars here and here prints out the logical content of the queue, and it used to be this, and I realized that I was missing cases that says, check if the queue is empty, or check if the queue is full, because in both of these cases you have to treat the thing specially, and this is things that I missed the first time around, and so it's worth being very careful. And that's the kind of stuff that is just too much hairy detail to expect anyone to do in the half an hour that you have in your exam. But doing it for real at least once gives you a deeper understanding of why that design with the -1 is something that I intuitively felt was a bit disgusting. Okay, it can be made to work, but it's a pain. Why is it a pain? Because in so many places you have to check for the -1, that in some cases you're bound to miss it out, because most of the time it works, except if you check that particular situation where, it wouldn't have worked there, and unless your test coverage is pretty extensive, you might not even notice that you have missed out one of the cases where you had to add some of this extra garbage over here. So I then went back and I implemented what I thought was a cleaner way of doing that, using something where instead of having 2 pointers marking the beginning and end of the used cells, there would just one pointer and a length, and this length could range from 0, saying there's no cells that are filled up, and the whole length of the circular array saying all the cells are filled up, and there's no ambiguity whatsoever, but it's all a continuum, and it doesn't have all the special cases that you have if you start making a pointer jump from the range of valid things to a number outside, which is -1. It could have been -666. It's something that is a discontinuity in the movement of the range. So the solution I'm talking about now, with a kind of one pointer and a length, is a better solution because there is a continuity between the values of the things that of the data fields that I'm using. So that's why it feels a lot cleaner, and actually the code does become a lot cleaner. If I compare the code that I had to write for implementing the solution with all these -1s and the one that I wrote for the solution where I am just using the one pointer and the length, and the other pointer is derived by having an explicitly stated invariant that the mhead plus size is modulo the length of the array is at all times equal to mtail. That's a nice invariant to have. It makes sense, and I can enforce it by deriving mhead by the inverse of this operation and so on. Then the code shrinks because all these, if mhead equal 1, if blah blah blah, all these things collapse and go away, and I don't have to do any of these special cases. I don't have to go through this code in detail. You will have written your own code. You will discover this by yourself. Anyway, by now this video is getting rather long already, and it could continue much further if we went into that kind of stuff line by line, but I think I've already lost most of my audience by now, as I said at the beginning, so I realize I should not overdo it. But before I stop, I want to share one more gotcha that bit me while I was programming all this. And so as I'm doing the circular buffer operations and I need to reduce my indices by modulo the size of my array, then if I say okay, the index is I modulo 10, so the modulo operation is like the remainder of the integer division, usually is represented with a percent sign. Okay, so if you say I percent 10, then you're reducing I modulo 10, and if you have like 15% 10 gives me 5, and 458% 10 gives me 8, just the last digit, because the remainder is going to be between 0 and 9. So is it always the case that the remainder is between 0 and 9? Well, what would be the value of minus 3% 10? I expected, and I wrote my code expecting that it would be 7, because that's the modulo 3 is in the equivalence class of 7 if we take the numbers modulo 10, which are all represented by the things from 0 to 9. Okay, and so minus 3 is equivalent to 7. And in more sensible languages, the minus 3% 10 actually does give 7. But I discovered, to my dismay, that in Java it returns minus 3. It's like minus 3 remainder of minus 3 divided by 10 gives minus 3. And okay, well, you can define the operator in a slightly different way, which returns the same things when the dividend is positive, but has this anomaly when the dividend is negative. And I acknowledge that you can have another rationale for why that is better in some cases, but it certainly confused me. And a bit of searching showed me that what I actually meant and what I needed to use in Java for the operation I wanted was a thing called math floor mod, which I have somewhere in my code over here. So math floor mod of this expression, mtail minus msize, which sometimes could be negative, reduced modulo the length of the array, then will give me something that is between 0 and length minus 1. Whereas if I had done mtail minus msize percent mdata.mlength, I would have received a negative value, which of course caused a bug, an elusive bug in my code. So before saying goodbye, I'll just give you a very small challenge. Please try to figure out exactly what kind of bug I might have had and write as many test cases as you think are necessary to highlight that bug if it's there. And then write some code that would recreate that bug. We're talking about a piece of code in the context of this FIFO queue that we've been working with that wraps around with the circular buffer, where if you wrap the indices around using the Java percent operator, then in some cases you get an incorrect result. But if you replace the percent with math floor mod, then you fix the bug. So unusually for a quiz, I've already told you how to fix the bug, and so your job is not to fix the bug. It is instead first to create a test that would spot the bug if it's there. Second, to recreate plausible code but which has the bug within this context. And third, to explain exactly when, precisely in what circumstances this bug would be triggered. Which of course logically comes before writing a good test. If you can explain exactly when it would be triggered, then you could write an excellent test. So you can do the steps in any order you like, so long as you do all three. Well, if you can do all that, then you got the spirit of a good programmer. I hope you enjoyed all of this stuff, and thank you very much for staying until the end. If you enjoyed this video, like it, share it with your friends, and subscribe to the channel for more. See you next time.